Hi, welcome to an audio test session with APX. These videos provide worthwhile information for APX users and demonstrations on a range of audio measurement applications. In this session, Joe demonstrates headphone testing.
Headphones and earphones have unique testing challenges because the tests must simulate the way they are used in practice, closely coupled to a listener's ears. This requires the use of some specialized test equipment. In this video, we'll cover equipment requirements, the head-related transfer function, headphone design target curves, and the importance of fit. We'll then do a demonstration of headphone measurements featuring frequency response, left-right tracking, total harmonic distortion, impedance, and active noise cancellation performance. One of the key equipment items needed for testing headphones and earphones is an acoustic test fixture. The one shown here on the right is a special mannequin called a head and torso simulator, or HATS. It's equipped with ear simulators. These are small couplers inside the mannequin's head that serve two functions. One, they simulate the acoustic impedance of a typical human ear, which is required to acoustically load the earphones, and two, each one has a built-in measurement microphone at the location of the eardrum within a typical ear, called the drum reference point, or DRP. A HATS like this also simulates the features of the outer ear, called the pinna, or pinnae in its plural form. This is important because many headphones and earphones interact with the pinnae in a way that can change their measured frequency response. Typically, an anechoic chamber is not required for headphone testing, but a room with low ambient noise is required, especially if you want to make measurements at frequencies as low as 20 to 30 Hertz, where mechanical equipment noise is present in many typical buildings. In addition to an audio analyzer, headphone testing requires a microphone power supply for each ear simulator microphone and a power amplifier to drive each earphone. The power requirement of the amplifiers is small, typically a few milliwatts and certainly less than half a watt, but you can't drive earphone transducers directly from an audio analyzer's generator. It's not designed to source that much current. In the demo for this video, we'll be using an acoustic test accessory called the APX 1701 transducer test interface, shown in the bottom of this photo. It has two precision power amplifiers and two microphone power supplies, as well as current sense resistors for measuring impedance. It's also fully integrated with the APX 500 software. Although a full head and torso simulator can be used for testing headphones, unless you're testing the microphone function of a headset, which we're not covering in this video, you can use a simpler and less expensive fixture than a HATS to test headphones. For example, this headphone test fixture has the same ear simulators as a HATS without the head and torso part of the mannequin, which is not relevant for headphones. It can be used to test all types of headphones and earphones, and it has the added benefit that it provides a high degree of noise isolation, which makes it ideal for testing headphones with active noise cancellation. Here is another type of test fixture called an ear and cheek simulator. It's functionally equivalent to the headphone test fixture, but only has one ear simulator, so it can be used to test one earphone at a time. Here's a similar fixture without the anatomically shaped pinna. This is useful for testing insert-type earphones that get inserted directly into the ear canal. As an alternative, you can also use the ear simulator without the fixture on the left. An important concept in headphone testing is the head-related transfer function, or HRTF. Suppose we have a loudspeaker with a flat frequency response, for example, if it was equalized flat. If we measured its frequency response with a measurement microphone in an anechoic chamber, a room with essentially no reflections, we would measure a flat curve like the one on the right. Now suppose we replace the microphone with a person at the same position, and instead we put a tiny microphone inside their ear canal, close to the eardrum. From the same perfectly flat loudspeaker, we would measure the response curve shown on the right. This curve is known as a head-related transfer function, or HRTF. There is actually a different HRTF curve for each position of the source around the person in three-dimensional space. This one is called the 0-degree or on-axis HRTF. The head-related transfer function includes the effects of the person's body, head, pinna, and ear canal on the acoustic signal as it travels from the source through the air to the eardrum. A consequence of this is that you have to account for the HRTF when considering the measured frequency response of headphones. There are a couple of ways to do so. One is to take the measured frequency response, apply the inverted head-related transfer function as an equalization curve, and then evaluate the result against the desired response. In this case, we would evaluate the equalized response in terms of how closely it matches a perfectly flat curve. Another approach is to use the concept of a design target curve. We start with the measured response curve and compare it to a design target, which has the head-related transfer function built in. We compare two frequency response curves by dividing their values in linear units or subtracting them in decibels. The result of this comparison is used to evaluate how close the measurement comes to meeting the design target. If the comparison curve is a flat line at 0 dB, as shown here, the measured response meets the design target perfectly. There can be many headphone design target curves. This graph shows three. The blue curve is the free field 0 degree HRTF we saw previously, which represents a completely anechoic space. The red curve is the HRTF for a diffuse field, an environment that is highly reverberant. In the distant past, both the free field and diffuse field HRTFs have been used for headphone design targets. But recent research from a group at Harman International has found that trained listeners prefer a curve like the green one, labeled Harman in the graph. Regardless of what design curve is in use, when testing headphones, it's important for the audio analyzer to have features like the ability to apply an EQ curve to the measured frequency response and the ability to compare the measured response to a design target. In the demonstration, we'll be using this headphone test fixture. First, we'll cover calibrating the ear simulators and measuring a metric called the headphone characteristic voltage. Then we'll go through some acoustic measurements, including frequency response, left-right tracking, sensitivity, harmonic distortion, and crosstalk. We'll also demonstrate impedance measurements and finally active noise cancellation performance. First, a note about the importance of fit. When testing headphones and earphones, the fit of the earphones on the test fixture can make a big difference to the measured frequency response, especially at low frequencies. Therefore, it's considered a good practice to make several measurements wherein the headphones are refit to the test fixture each time and then average the results. A power average is used, which averages the signal power or level squared at each frequency across all datasets. And a note about headphone impedance measurements. In most headphones, the left and right earphones share a common ground. This can cause problems when measuring the small current levels present, so we found that it's best to measure one earphone at a time by disconnecting the other one from the circuit. To make this easier, we made this switch box, which enables switching to one headphone or the other. For convenience, it also has a male XLR connector for connections to sense the voltage across the earphone. To demonstrate measuring the insertion loss of active noise cancellation headphones, we're using a setup like this. The headphone test fixture is positioned between a pair of stereo speakers being driven with pink noise to a level well above the ambient noise floor. Using the ear simulator microphones, we'll first measure the level of the pink noise signal with the open ear. Then we measure the noise level with the headphones in place but the ANC feature turned off to determine the passive noise attenuation. Finally, we repeat the measurement with the ANC switched on to measure the active attenuation. Here is our APX project file for headphone testing. The project file name is Headphone Test Demo version 6.0. As you can see, it has several signal paths. The first is named Signal Path 1, Cal Ear Simulators. Next is Signal Path 2, Acoustic, then Signal Path 3, Impedance, and finally Signal Path 4, Noise Cancellation. The project also has 4 sequences named Cal and Regulate, Acoustic Measurement, Impedance Measurements, and ANC Measurements. And you may remember from other videos in this series that a sequence is really just a collection of checked items, signal paths, measurements, results, and sequence steps. For this demo, I'm going to run each sequence separately and then step through the sequence items to show how the test is implemented. Let's go ahead and run the Cal and Regulate sequence. First, we get a prompt with instructions on how to connect the audio analyzer to the device under test. I'm using an APX 515 audio analyzer here with an APX 1701 transducer test interface. The operator is presented with instructions on how to make the various connections. We have the 2 power amplifiers driving the left and right headphones. We have the 2 ear simulator mics connected to the CCP microphone inputs. The analyzer output channels are connected to the power amplifier inputs, and the mic pass-throughs are connected to the balanced analog inputs on the audio analyzer. Next, we get a prompt to calibrate the right ear simulator. Here we're using a sound level calibrator that generates a sound level of 114 dBSPL at 250 Hz. Note that without the calibrator present, this field showing the measured frequency is red. That's because I've configured the system so that the expected calibrator frequency is 250 Hz. As a result, when only noise is present, the measured frequency field is highlighted in red as a warning. If I did click the OK button at this point, the sequence would fail because the measured calibrator frequency is not within tolerance. I'll go ahead and slide the calibrator over the right ear simulator and turn it on. Over in the FFT monitor, you can see a nice sharp peak in the red trace at 250 Hz. With the calibrator on, we're seeing a measured sensitivity of 16.5 millivolts per Pascal. Notice that the level meter behind the dialog is currently reading 118 dBSPL, not 114 as it should, because the value has not yet been committed. When I click OK, the sensitivity value is committed and the level meter changes to the correct value of 114 dBSPL. The same procedure is followed to calibrate the left ear simulator. Once the calibration is complete, we get a prompt to install the left and right pinna on the ear simulators. The next prompt is an instruction to place the headphones on the test fixture. After carefully placing the headphones on the fixture, I will dismiss the prompt. Here the audio analyzer is performing a regulation step. The regulation target is the generator voltage that will produce a sound pressure level of 94 dBSPL at 500 Hz. In IEC standard 60268 Part 7 on headphones, this is known as the characteristic voltage. We've set the target channel as channel 1, the left ear simulator. When the regulation step finishes, the analyzer sets the generator's 0 dBRG reference to the required level. As a result, for any measurement in the same signal path, you can conveniently set the generator level to 0 dBRG to have it generate the characteristic voltage. Let's look at how this is implemented. In the signal path setup node, we can expand the sequence steps node to see 3 prompt steps. First, we have the connections prompt. We can preview it to see what the prompt will look like. Next is the prompt to calibrate the right ear simulator. The preview shows us what the prompt will look like. The key thing about this prompt is that the Set dBSPL checkbox is checked so that the microphone sensitivity will be assigned to channel 2, the right ear simulator. An alternative to a sound level calibrator can be used if your equipment supports it. The ear simulators in this test fixture have what's called a Transducer Electronic Data Sheet, or TEDS. This stores the microphone calibration data in a chip inside the microphone preamplifier. On supported hardware, the audio analyzer can read the TEDS data and use it to set the mic sensitivity. To use it manually, click the Calibrate from TEDS button, choose the TEDS source, and then click the Read TEDS button. You can assign it to one of the input channels by selecting the channel and clicking Set Sensitivity. There's also a sequence step to do this automatically. Another feature we've used here is in the signal path setup node of the acoustic signal path. If we open the Measurement Sequence Settings node, you can see that the Auto Set Generator Level checkbox is checked. This causes the regulation to be performed when the signal path setup measurement is run. Regulation settings are accessed from the Auto Set Generator Level button in the References control group. The settings here regulate the RMS level to a target value of 94 dBSPL at 500 Hz on channel 1 and set the dBRG reference accordingly. This corresponds to the characteristic voltage. Next, we'll run the acoustic measurement sequence by selecting it and clicking the Run Sequence button. First, we get a prompt with an instruction to place the headphones on the test fixture. In this sequence, we will measure the headphone frequency response 5 times after refitting the headphones on the fixture each time. The headphones are still in place, so I'll just click OK. Each sweep is 2 seconds long, but we've sped up the video here for efficiency. Once the 5 appended frequency response measurements are complete, we measure crosstalk right into left, and then crosstalk left into right to finish this sequence. Now let's go back and look at some of the measurement results in acoustic response. First, we have the primary result, RMS level. Here you see the 10 traces from the 5 appended measurements with refitting the headphones before each measurement. Next, we have a derived result named RMS Level Average with 2 traces on it, one for the left earphone and one for the right. Each trace represents a power average of the 5 datasets for an earphone. This is sometimes called a spatial average. It attempts to account for measurement variation due to the fit of the headphones. This next derived result is called left-right track. It compares the fit average data of the right earphone to that of the left earphone. For perfectly matched earphones, this curve should be a flat line at 0 dB. As you can see, these headphones are fairly well matched. We've added limits in the frequency range from 100 Hz to 10 kHz to this result. This next derived result is called average response 500 Hz to 2 kHz. Here we have calculated a power average of the data for each earphone in the mid-frequency range. It's a measure of the sensitivity of the earphones. One of the advantages of the log-swept sine or chirp stimulus for audio test is that you can measure harmonic distortion and RMS level versus frequency simultaneously. This primary result is called level and distortion. It shows the fundamental level response, the total harmonic distortion, and the second and third harmonic distortion products all on the same graph. For these headphones, the total harmonic distortion, the purple trace, is dominated by harmonic H2, the red trace. This is an EQ-derived result. Here we have applied the inverse of the Harman target curve as an EQ to the 5 level measurements of the left earphone. If the earphone matched the target curve perfectly, the response versus frequency would be a flat line. In this result, the equalized responses have been power averaged and offset, such that the mid-frequency values are at 0 dB. This earphone matches the target curve fairly well in this frequency range, but deviates at higher frequencies. This primary result shows the acquired log-swept sine chirp waveforms for the 5 appended measurements on the left and right channels. Now let's look at a crosstalk measurement. Here we are using an acoustic response measurement, but generator channel 1 has been disabled. This means the right earphone, the red trace, is driven, and any signal above the noise floor measured in the left earphone, the blue trace, is due to crosstalk. A compare-derived result is then used to calculate the ratio of the response between the left earphone and the right earphone, which is the crosstalk. I used this method because it's easy to measure the level of the crosstalk signal above the noise floor. Now let's run the impedance measurement sequence by selecting it and clicking the Run Sequence button. First, we get a prompt to make the required connections. The impedance measurement requires different connections, which I've already configured. One earphone is being driven through the switch box I described earlier. One input channel is used to measure the earphone voltage, and the second channel is used to measure the current. Next, we get a prompt to set the switch box switch to the tip position to drive the left earphone. When the prompt is dismissed, the impedance measurement is run for the left earphone. The next prompt instructs us to set the switch box switch to the ring position to drive the right earphone. After setting the switch, we dismiss the prompt to proceed with the impedance measurement of the right earphone, which completes this sequence. Let's take a closer look at the impedance measurement results. Here we have the impedance magnitude. The processed version of the measured curve is shown in blue, and the curve fit to the data, which in this case is set to fit from 20 Hz to 1.6 kHz, is shown in red. And here's the impedance phase result. Now we'll run the Anc measurement sequence by selecting it and clicking the Run Sequence button. First, we get a prompt to make the required connections. In this case, we are testing headphones with active noise cancellation. The analyzer is driving a pair of stereo speakers with a pink noise signal, and we are measuring the signals from the ear simulator microphones. We will measure a 1/6 octave spectrum for 3 conditions: open ear, passive attenuation, and passive plus active attenuation. Next, we get a prompt to remove the headphones from the test fixture to prepare for the open ear measurement. In this step, the system will measure 10 seconds of the pink noise signal in the open ear condition. We've sped up the video here for efficiency. This prompt, for the passive measurement, instructs us to place the headphones on the test fixture with the ANC function switched off. Again, the system will measure for 10 seconds. This prompt instructs us to switch on the active noise cancellation feature. Another 10-second measurement is conducted. This result shows the octave spectra for the 3 measurement conditions for the left and right earphone. To make sense of this, we'll use a compare-derived result to normalize all three measurement results to the open-ear measurement result. Here's the compare-derived result that shows the passive and active attenuation for the left earphone. The blue curve is the open-ear measurement compared to itself. It constitutes a type of reference for the open-ear condition. The red curve is the measurement without ANC compared to the open ear. This represents the passive attenuation. As shown, the sound level actually increases at low frequency due to the resonant cavity formed by the earphone on the ear, sometimes called the conch or seashell effect. The green curve shows the active plus passive attenuation. As you can see, the ANC function adds significant attenuation at frequencies up to about 1.5 Kilohertz. Here's a similar comparison curve for the right earphone. This concludes our audio test sessions with APX video and headphone testing. Thanks for watching.
Thank you for joining us for this audio test session with APX. For additional videos, visit ap.com or any of our social media channels.